Hello, everyone. And this is week 2 of our live discussions for this NPTEL course, Adaptive, Nonlinear and Adaptive Control, taken by Professor Shubhendu Bhasin of IIT Delhi. Now, in this course, we would be studying various methods of adaptive control and how different systems are controlled under uncertainties in the system dynamics. Now, in the previous week, we covered a lot of ground and we had various good questions in this uh, uh, live discussion sessions. And you are welcome to join each Friday, as we have mentioned in the link. And these videos would be uploaded to my YouTube channel for later uh, easy perusal for you during your later stages of your learning. And without further ado, I wanted to show a few examples of how adaptive command tracking or some of these concepts which you have covered up till week 3 of this course, how they are applicable in real world, and so we would see some examples as well. So without further ado, let me switch over to my notes app, and we could do that. Sorry. I hope you can see my screen. If you do,
Yes,
please
sir.
tell me.
Yes, sir. Yes.
Okay. So your question was to show a few examples on how these approaches are implemented. So let's look at a quick example, which is a very common example in adaptive control literature. So it's a very simple one. So let's start from there and we can move up our ways. So the concept is a one-link robot manipulator. Now, I want to ask you, do you have any idea regarding what are manipulators?
No, sir.
Okay, so do you have idea about robotics and what it does? I
No, sir.
mean,
No,
a
no, no.
basic general idea, in fact.
Yes, sir. Yes, sir. Basic general idea I am having.
Yeah, I'm not talking about like mathematical per se, but a general idea of robotics. I hope everyone has. We have seen various robots in movies and whatever, right? So we would be talking about a single link robot. And what is link? What do I mean by link? Is this kind of, suppose there are two rod-like structures which are connected by this hinge over here. This is a hinge, right? Or whatever it is
Yes,
called,
sir. Yes, sir.
joint,
Hinge. Yes, sir. Joint.
right? So these two are called the links, right? These two are called links, and this manipulator is joined to the ground, let's say, um, at this point. So this is your ground. Pardon my bad handwriting today. So yeah, so these are two. This is a two-link robot manipulator, two-link robot, and what we are talking about right now is a very simple case, which is a one-link manipulator. So we have this kind of. I think you can mute yourself as of now. There is some noise from your end. I could ask you to turn on your mic at a later stage when you have a doubt. Okay. Yeah, so this is a single link robot manipulator which is attached to the ground here, and it is free to rotate about this joint. Okay. Now there is a reference over here, let's say reference line, which is an imaginary line over here, and you are theta degrees or theta radians apart from this reference line, right? Now, this link over here, this link over here has some moment of inertia, right? So moment of inertia is essentially how the mass equivalent for rotational motion. So it has a specific moment of inertia, and it has some length L. Right? Now, what you have to do is you have to apply a torque. Uh, your objective is to apply a torque about this joint. That torque is denoted by tau. In the objective is to bring this tip of this manipulator down to this reference line, and you have to bring it over to here. So the dynamics of this system is given by this equation, and I would be explaining this equation in a little bit. So if you remember the linear case or the rectilinear motion case of a mass spring damper system, you had this mass which was acting on it a force, and this was a mass, and this is the spring constant K, and there was a damper connected to it. The equation of motion for this was similar, right? So there was mass into acceleration, which was mx double dot, plus the damping, let's denote it by b, b into x dot, plus k into x was equal to the overall force applied, right? In similar fashion, in the rotation case, there is this kind of moment of inertia kind of thing, which is equivalent. Let me not write approximately. It is equivalent to mass and this was the equivalent damping. Could you give me 2 seconds? Yeah, I'm back. Sorry for that. Uh, so this is the equivalent to damping, and this is the component acting due to gravity, right? Because the gravity is in this direction, acceleration due to gravity, and this gravity is acting on the center of gravity of this link, and it's pulling it down. So it's an effective torque application on in this direction, right? So if you look at this equation of motion over here, can you hear me?
Yes,
Or
sir.
did I?
Yes, sir.
Yeah,
Yes,
yeah.
sir.
Okay, so if you look at this motion of equation, so what is your state in this equation? Could you figure out what is the state?
Q, sir. State variable Q,
Yeah,
and X is the displacement or rotational angular displacement we can think of.
yeah. So there is this state Q. Is there any other state in this equation?
The X, this is Q dot, sir. Q dot is also state.
Q dot is also is a state, right?
Q double
So
dot
it's a
also.
actually no. q double dot is not a state. Actually, there are only two states, and q double dot is the derivative of this state,
Yes,
q
sir.
dot. If you had considered
Correct, sir.
q double dot as a state as well, right? There wouldn't have been any derivative equation in this. So it is not a differential equation, it would have been an algebraic equation. So we want a first order differential equation. So we have to consider one shy of the entire thing. So q and q dot only. So this is your angular position. And this is the angular velocity. Right? Now, let's look at uh, a command tracking problem. So what is a command tracking problem? Do you remember in the previous live discussion, we had covered two problems. One is a regulation problem, and one was a tracking problem. Now, regulation problem meant that the states must go to zero. You have to design your control in such a way that the states go to zero. And another problem is so-called tracking problem, wherein the states must go to a desired reference trajectory. So suppose you have a desired trajectory, which is q desired and q dot desired. So it could be like that. So you want your system trajectory to track a sinusoid, let's say, and your q dot would be a cosine wave. It could so happen, right? So this trajectory is defined by the user. Okay. So now how do we do this? Now in this problem, we assume that a few components are unknown. Few components unknown implies, like, suppose that this b vector, b value is unknown, this mass is unknown, let's say, and this L is unknown, right? So this is a problem of an adaptive control framework. Suppose if everything was known, then you could design a control using nonlinear control. So that was the parlance in the nonlinear control. But if some things are unknown, then how do we do this things? Okay, so in order to do that, we first look at if everything was known, what would have been the control law, right? So assuming everything was known, every parameter, namely the I, the mass, the friction, damping coefficient, the acceleration due to gravity, and the length, everything was known. Then what happens? So uh, in this in this framework, we talk about this concept of error or tracking error. Okay. Now, what is tracking error? Tracking error is nothing but the difference in between the two states, q and q desired, right? Now, if, yeah, come again.
Yes, sir. Yes, sir.
Okay. So this is the tracking error, which we defined it to be like this. Now, what we do is we compute the derivatives of the tracking error. So E dot is essentially Q dot plus, sorry, Q dot minus Q dot desired. Okay. And the double derivative of E is Q double dot minus Q D double dot. Okay. Now we assume that this reference trajectory, its first derivative and the second derivative, everything is known. known and it is defined by the user. Okay. So we now focus on this equation because it contains this q double dot, which was part of our dynamics. So this dynamics contains the term q double dot. So we are differentiating up to q double dot. Okay. Had it been the the differential equation was up to 3 derivatives, we would have computed till 3 derivatives. Okay. Now we what we do is we multiply both sides by the moment of inertia, because our original dynamics contained this term I into q double dot, right? So what we do is we multiply both sides by I, or the moment of inertia, and we obtain I q double dot minus I q d double dot, right? Now what we can do is we can substitute this entire dynamics into this. We take this entire, so this essentially becomes minus bq dot minus mgl sin q plus tau. Okay. Now we can write this integration, no, sorry, error dynamics as IE double dot is equal to minus BQ dot plus, sorry, not plus, minus MGL sin theta, sorry, sin Q plus tau minus IQ desired double dot. Okay. Now we have assumed that everything is known, right? So how do we design the torque input such that the error, time error, goes to 0 as t tends to infinity? How do you design that? So I pose this as a question to you. So can you propose a controller so that the error goes to 0?
Yes, sir.
Uh, tell me. Tell me one proposal.
Plus BQ
Okay, so tau is equal to
plus
PQ,
BQ.
PQ
Uh,
dot, right? So this was dot.
BQ dot, yes, sir.
Okay.
Plus MGL into sine uh, G, sine
Thank
Q,
you. Sorry.
sine
So
Q.
my
Yeah,
handwriting is
and
very bad today.
also we require I double dot must be asymptotically stable for that. Mm, I double dot is equal to,
No, so if you provide the information of IQ
yes, sir.
double dot,
Yes, sir.
IQD double dot in the controller, then you could easily cancel it out over here. So you don't need this QD double dot to be asymptotically going to 0. You can easily cancel it out, right? Okay. So just this control will suffice.
Sir, while designing the controller in sliding mode, we cannot take nonlinear parts in designing the controller of equivalent parts computation. So in such case, we can do not take uncertainties like MGL into sine theta.
Uh, as of now, we have not considered any uncertainty, right? So you can actually cancel out all these nonlinearities which you have in your control law. So this is called a feedback linearization approach,
Yes, sir.
right?
Yes,
So
sir.
this is not a sliding mode controller, to mind you,
Yes.
because sliding mode controller there is another variable of sliding surface, right?
Yes, sir.
Uh, Here we are just having a differential equation, and we are placing our control law in such a way that we cancel out the nonlinearities, and
Yes.
we also add or specifically subtract some k1 into E minus k2 into E dot. Because if only these nonlinearities were considered, the right hand side of this would have been 0,
Yes,
and
sir.
we couldn't talk about the error going down to 0 if the derivative is 0, right? So we have to place these two components, so k1 into E minus k2 into E dot. Now, if you look at this, it's simply like a PD control, right? Proportional into derivative component. So
Yes.
just to give you a brief context, so PD control or PID control is a general framework of linear systems control, wherein the error and the integration of error and the differentiation of error, these three signals are fed to the controller, and each of them are multiplied by some constants kp, ki, and kd, and the control action would be the summation of all these three terms. Now, this PID controller, actually, I assume that you know this, but still for completeness sake, I'm just mentioning this. The control law is given by this, and if you choose some good values of Kp, Ki, and Kd, the system or the linear system which it acts on would be stable. So this is a brief background on PID controller. So I just wanted to mention it for completeness sake. So this is similar to that. So we have this tracking error. This is a proportional component of it, and this is the derivative component of it. Now, if you have this kind of control law, if you substitute the values of this control law in this dynamics, we would have this IQ, sorry, IE double dot is equal to minus K1 into E minus K2 into E dot, right? Now,
Yes. Yes, sir. Yes, sir. Understood. Yes.
yeah. So is the system stable? What
Okay.
can you say about this system?
So we can find out the eigenvalues by since it is a differential equation, we can say all eigenvalues are in the left half of S plane, so that the system is stable.
So if you look at the E dot and E double dot, it is essentially written as 0, 1, uh, minus K1 minus K2
Yes, sir. Yes.
into E and E dot. So for this to be stable, this matrix must be Hurwitz, or in other words, the eigenvalues of this matrix, let me call this matrix A, lambda A must be, all of those eigenvalues must be less than 0. So this is one approach of studying the stability. Now we already have a generalized approach of studying stability, which is known as Lyapunov analysis, right? So Since we have been studying this Lyapunov analysis a lot, can you propose a Lyapunov function such that the differentiation of that Lyapunov function is negative definite?
Sir, can you repeat, sir?
Yeah. So since we have considered this Lyapunov analysis in this whole course, so this approach, the left hand side approach, is valid and it's very good approach for linear systems. But what if this system was not linear? So what if uh, this output equation which came out was nonlinear? So we would have studied the stability based on Lyapunov analysis. So uh, I can propose a Lyapunov candidate Lyapunov function such that uh, this system over here was stable. So if I take it over here, I can propose a Lyapunov function which is based on the E and E dot to be, let's say, I'm deliberately choosing it as like this because it's actually good for us. So if you compute the differentiation, so is this positive definite function?
Yes, sir. Yes, sir. Positive definite.
It is positive definite.
Positive definite and radially unbound also.
Radially
Based
unbounded. Good.
and decreasant, we can say. Maybe.
Decrescent.
Yes, sir.
Okay, perfect. So decrescence, since this Lyapunov function is not time dependent, right? So
Yes, sir.
decrescence doesn't play a role here because all results are uniform
Yes, sir. Yes, sir.
in the autonomous case. So decrescence doesn't play a role, but since it's very good to mention decrescence as well. Okay. So we can compute the differentiation of v dot to be right. Now, if I substitute IE from here, we have E dot, right?
Yes, sir. Yes, sir.
Now I can simply cancel out these two terms and obtain minus K2 E dot square. Now what kind of function is this? Is it negative
Sir,
semi-definite, negative
sir,
definite?
actually, E dot into I is there.
Yes, sir. Yeah, E dot into IE was there, right?
Yes, sir.
This was there, right? So
Yes.
I have substituted IE double dot from this expression.
Okay, okay. Yes, sir. Yes, sir.
Okay. Now this
Yes, sir.
V
Yes.
dot is minus K2 into E dot squared. So is this negative definite or negative semi-definite? It is
Into
negative.
semi-definite, sir. This one. Why? Because it
Okay.
is a function of only E dot only.
Perfect, perfect. So it is NST. So there was a comment on the previous week's lecture YouTube video, right? So there was a similar comment on how this is negative definite or negative semi-definite. And just for completeness sake, let me mention that again. I had explained it in the comment section as well. But for completeness sake, this Lyapunov function, the original Lyapunov function, is both a function on E and E dot. So if you look at this function, which is the output, it is only a function of E dot over here and not on E. So if we consider that E and E dot, suppose E was any value, let's say I have 10 and E dot is 0, if you substitute it over here, uh, then the output would be 0. But this is not the origin, right? This is not the origin. And according to the definition, negative definite function must be 0 only at the origin, and it should be negative everywhere else.
Yes,
So
sir.
this is not negative definite, but it is negative semi-definite. So at best, we could comment about stability and not asymptotic stability, right? But there is a beautiful theorem, which is Lassalle's theorem, right? And by using Lassalle's theorem, we could show that the origin is asymptotically stable as well. So how do we do that? Now, the theorem of Lassalle's, could you let me test you out? What is the theorem of Lassalle's theorem?
No, sir, I don't have idea. Can you please repeat that, just that theorem?
Okay.
Lisa,
Yeah. So give me two
sir, what
seconds.
is the spelling? I don't know pronunciation. I could not able to get it properly.
So it was covered in the previous lectures. Yeah, could you find it?
Yes, sir. Yes, sir. Lascelles theorem.
Yep. So let me mention that for completeness sake, and then we could talk about it. So suppose there is a set omega, which is a subset of the original domain of the function, right? Now, suppose this omega is a compact set.
Sir, this was not covered in the basics, sir.
Oh, okay. Wasn't it? Okay. Uh, so this would be a new concept then. So
Yes, sir.
we actually use Lassalle's theorem in studying the stability or uh, asymptotic stability of the origin in nonlinear systems. Okay, so Lassalle's theorem says that if there is a set uh, so if there is a set omega which is the subset of D, if it is compact and positively invariant, so positive invariance means that if the trajectories of state start within this omega, they stay in this omega. Okay. So I would be drawing a picture a little moment from now, and this would clear everything. So if there is a set E, which is or D, such that the Lyapunov function is 0 and M is the largest largest positively invariant set in E, then if you start from omega, U would converge to M. Now, this is a very interesting concept. So let's look at a pictorial representation, and things would make sense from there. So if you have a set omega, right, and there is a subset which is called E, right? E denotes that the Lyapunov function is identically equal to 0. Okay. And there is a smaller subset M where it says that it is the largest invariant set of E. So invariance means that if you start within that set, it implies that xt is in M for all t greater than t0. Okay, did that make sense? The invariance. Did this portion make sense?
Yes, sir. Yes, sir.
Okay. So what I mean to say by this is that this is the largest invariant set. So there is no other set M prime wherein if you start from M prime, you stay in M prime. There is no such set there. So M is the largest possible invariant set in E, right? If that happens, any trajectory which is outside here, it would eventually converge to M. So
Sir,
let's,
actually, we have Lyapunov definition is also like this only, no, sir. There exists an epsilon set and a delta set, such that for every given epsilon, there exists a delta set, and initial conditions within this delta will should not leave the epsilon region.
yeah. So the key difference there was, uh, suppose this is the epsilon set, the delta set can be this, right? So if
Yes,
you
sir.
start from here, it would go and venture out to here.
Yes, sir. Yes, sir.
So
It should not
this,
leave. Yes, sir.
yeah. So but there is a difference. This is the opposite one. So in this case, there was an outward going fashion, but
Yes.
in this there is an inward pointing thing.
Okay, okay.
Yeah.
Yeah. Yes, sir.
Now
Yes, sir.
let's look at how this theorem is used to prove asymptotic results. So if you look at this, right, this v dot is equal to minus k into e dot squared, right? If I look at over here, if I keep this over here, was it k2 or k1? K2. Yeah. So let the omega be equal to the r squared. R squared, why? Because there is this e and e dot. Okay. Now, what is e? E was this larger set wherein the function which we are considering is equal to 0, right? So this must be equal to 0. So E contains all the elements x in R2 such that minus k2 e dot squared is equal to 0, right? So what are these elements? It is only possible when e and e dot, e can be any value, but e dot has to be 0, right?
Yes, sir.
Okay, so this capital E set contains all the possible states where E can take any value, but the E dot must be equal to 0, because this V dot must be equal to 0, right? Now let's compute what is M. So M is the largest invariant set in say in E, sorry, is equal to largest invariant set in E. Now what does it mean to be invariant? Is that largest invariant set in E. So uh, for an element to be in E, the E, this x should be of this form, right? Now, if I compute the x derivative is equal to E dot and 0, that x derivative must be also 0, because we are trying to find out what is the invariance set. So if a set is said to be invariant, the derivative must be equal to 0. So it doesn't need to change from its value, right? So E dot must be equal to 0. This is a long form way of saying E dot is 0. Now, if E dot is 0, if E dot is 0, right? And E double dot is also 0, then according to our original dynamics, which was over way back over here, if E double dot was equal to 0, then E and E dot must be equal to 0, because for any value of k1 and k2, this equation must hold. So if E double dot is 0, then E dot and E dot must be 0. E and E dot must be 0, right? So the largest invariant set was this only single value, which is E is equal to 0 and E dot is equal to 0, which is the origin, right? So till here, did it make sense?
Can you elaborate the things, sir, now?
This portion, right? This portion, right? So up till
Yes.
here, was it okay, right? So this
Diagram also, sir. Diagram also. Oh,
okay.
can you repeat, sir? Diagram also you have shown that. Yes, sir. Yes, sir. Yes, sir.
Okay. So in this example, we had this capital E, which is the places where the value or the V function, V dot function is 0, right? So the
Sir.
places where V function is 0, the error and error dot, error can be any value, but E dot can be, it has to be 0. Did that make sense?
Yes, sir. Generally, a straight line where E dot is 0 is applicable for this kind of solution, sir.
Right.
E dot is 0 line where E is continuously changing.
Yeah, yeah, exactly, exactly, right? So there is a, if you look at this two-dimensional case, right? So
Yes, sir.
E
Yes,
dot and E, so this entire line, this entire green line
yes, sir. Yes, sir.
is the
Yes, yes, sir. Yes, sir.
area, right? So suppose I start from here, right? What it says that in this in this zone where E can take any value, but E dot is 0, here everywhere this V dot is equal to 0. V dot is equal to 0,
Yes,
right?
sir. Yes, yes, sir. Yes.
But outside this line, there is a tendency to come down to or this line, right? If you start anywhere, there is a force, let's say, which is minus k2 into e dot squared, right? It is applying over here. So anywhere we are starting, we are trying to go down to this line, right?
Yes, sir. Yes, sir. This is Lyapunov function, sir. K2 into E dot square means.
Exactly, exactly. V dot was minus k2 into e square, e dot square, right? So this was the derivative of the Lyapunov function,
Derivative.
right?
Yes.
Now, as you decrease the Lyapunov function, the state moves, right? So if you move the state, the Lyapunov function is decreasing. Now, the state has a tendency to go down wherever you are in the outside this line. It has the tendency to move towards this line.
Yes, sir. When E dot
But
is decreasing. Yes, sir.
E dot is equal to yeah. At E dot is equal to 0, there is these points in the line, right? So any point in this line has E dot is equal to 0, right? And which would be the NSD result, right? So V dot is equal to 0 over here, right?
Yes, sir.
Now we have to show that the origin, all these points, if suppose the trajectory comes down to here, we have to show that it goes to 0 eventually. That is our objective.
Yes, sir. Yes, sir. It should reach equilibrium point. Yes, sir.
Yeah, exactly. So that would be asymptotic stability result, right? Till now we have this result which is stability result, not asymptotic stability result, right? So how do we show that the origin is convergent, like the trajectories are converging to origin? So herein lies the Lassalle's theorem. So if you look at this pictorial diagram which I have drawn in the E and E dot case, right? The trajectories, this entire region, the outside region, entire T is this omega, right? And this line, the green line which I had, is this capital E.
Yes, sir. Yes, sir.
And if I show that the origin is the only element in M,
Yes,
then
sir.
by Lassalle's theorem, if I start anywhere from omega, I would reach M surely.
Yes, sir. Yes, sir.
So this is the intuition of Lassalle's theorem. Now we show how it is done,
Yes, sir.
right? So the concept is that no solution to V dot is equal to 0 can stay identically to the same point, right? Other than origin. This implies, suppose if I have the solution over here, this solution cannot stay here for future time. It has to decrease or it has to move at least. So this is what is meant by the largest invariant set of E. No solution to V dot x is equal to 0 can stay identically to the same point. and the only solution that does so is the origin. If that is the case, then the origin is said to be asymptotically stable, even if the Lyapunov function was NSD. This is the beauty of Lassalle's theorem. So even if this Lyapunov function derivative was NSD, we could still show an asymptotic result. So here is how we do it. So as you saw that uh, suppose there is a solution E and E dot which satisfies this V dot is equal to 0. This implies E dot was equal to 0, right? Now no solution E dot being equal to 0 can identically stay there. So E double dot cannot be equal to 0, right? For any other value except the origin. So let's
Yes, sir.
see what are the values where E double dot is equal to 0. So E double dot is equal to 0 implies that I E double dot is equal to 0, which was minus K1 E dot, sorry, minus K1 E minus K2 E double, sorry, E dot is equal to 0, right? And E dot was also 0, right? Because this was the point over here. So E is also 0. Did that make sense? So E dot was equal to 0 because we have said that the point must lie in this E region. And if point must lie in E region means that E dot is equal to 0. And we have to find the point which we have found that doesn't identically remain there. So E double dot must not be equal to 0. So if we find out where are the points where E double dot is equal to 0 and E dot is equal to 0, this only leads to the conclusion that E is equal to 0. And E equal to 0 and E dot is equal to 0 is the origin. So the largest invariant set M is the origin. So if you come to this line, you are bound by law to move from this point and go down to origin. So this is the whole picture where even if the Lyapunov function is negative semi-definite, you could show an asymptotic result because the origin is convergent. Did that make sense?
Yes, sir. Yes, sir.
Okay. So you have a new tool in your arsenal, which is the Lassalle theorem. I thought that Professor Bhasin had covered this in the lecture, but I might have been mistaken. Okay. But still, this is a very good concept. And if Professor Bhasin didn't cover this, I don't think this would come in your assignments or examinations. But still, for completeness sake, we have covered this. Is that okay?
Yes, sir.
Okay, so it was a very long detour from this original expression, right? So if you look at the original expression, this, right? So this was essentially stable. And we saw a very simple way of seeing how it is stable. If we choose this K1 and K2 such that this matrix is Hurwitz or the eigenvalues are less than 0, then we could show this. Or we could have this entire Lyapunov discussion, which taught us this Lassalle's theorem, which is very important in adaptive control literature. So this Lassalle's theorem gives like a very generalized way of studying these uh, approaches, and we can show that the origin x0 is asymptotically stable under some k1 and k2. Okay, so let's look at how so this entire thing was done based on the assumption that all these values I, M, G, L, and all these parameters were known. right? Now, how do we do these approaches, deal with these approaches when the parameters are unknown, right? That was the question, right? Yeah. Can you hear me now?
Yes, sir.
Okay, so this was the assumption before. Now let's look at the case where these parameters are not known, right? So if you go to the original equation over here, let me copy it over here. Okay, so this was your expression, right? Now, what we do is we add this concept of filtered tracking error. Why do we do this? It would be clear in a moment. Now, what is a filter tracking error? Filter tracking error is this concept of E dot plus alpha E, right? So R, let's say we define this tracking error, filter tracking error, R is equal to E dot plus alpha E. Now, why we do this is simple. Since there is two states in this system, right, E and E dot, the analysis always involves a vector, right? So there is this vector E and E dot. So if you consider uh, this vector to be X, let's say, so the entire analysis would revolve around these X terms, right? But the filter tracking error provides an approach to combine these states together, right? So it combines these two errors together by adding this alpha term, which is a gain, which is defined by the user. Okay. Generally, it is taken to be 0.1, zero point 0.5, whatever. Okay. This can be tuned. Now, the interesting thing is that if you show that R goes to 0, it can be shown that E also goes to 0 and E dot also goes to 0. Okay.
Yes, sir.
Okay, so this is the concept of it. You can actually show it from calculus, but I'm not going into that as of now. But this is the reasoning behind why we choose this filter tracking error, because we want a scalar value which is showing us our uh, performance, so to speak. So what do we do is we take the original system, which was like this. right? And we take the filter tracking error r is equal to e dot plus alpha e, and we compute the first derivative of this, which was e double dot plus alpha e dot. Okay. Now what we do is we multiply both sides by this moment of inertia matrix I dot is equal to I e double dot plus alpha I e dot. Okay. Now substituting this I e double dot from here, I can write I r dot is equal to minus b q dot this thing plus alpha I e dot. Okay. So up till here, is it okay?
Yes, sir.
So up till here, is it okay, right? So this is the filter tracking dynamics. Filter tracking error dynamics, right? Now we have assumed that,
Sir, can we get these notes, sir?
yeah, I would share that. I would share that.
Notes only, sir. Actually, entire video means again I need to spend 2 hours.
Yeah, I would be sharing these notes as well. Yeah. I forgot to do it in the previous lecture, but I would be consolidating these two lectures and sending it to you via mail.
Yes, sir.
I should have done that last week as well, so I forgot that. Okay.
Thank you.
Yeah. So we assume that B, M, L, I are unknown. Okay. Now we take a moment to step back. Why means how powerful this approach is. We are not assuming any values on the moment of inertia, mass, length, and the damping. So this is very generalizable. So if you have a single link robot, any length, let's say there is a small robot of 10 centimeters versus a large robot of 10 meters. The control law which you develop over here would act similarly on both these approaches. So this is the beauty of adaptive control. Okay, so enough chit chat. So these parameters are unknown, right? So let's uh, do what is called a separation of parameters, right? So we have certain parameters which are multiplied by this state functions on state. So what we can do is we can separate these out from its uh, from the states, right? So I can write IR dot is equal to minus Q dot minus GL sine not GL minus G sine theta G sine Q uh, minus QD double dot plus alpha E dot. What I'm doing is finding out a matrix representation of the uncertain parameters and the certain parameters. Right. So if you look at this, so minus q dot is multiplied by this b, minus g sine q is multiplied by ml, and minus q d double dot plus alpha e dot is multiplied by I, right?
Yes,
Hello.
sir. Yes, sir. Yes.
Yeah. So this is known to you, and this is the unknown component.
Okay. We are making in the form of theta and phi transpose like that, sir.
Exactly. Yeah. Plus tau. The tau is also here, right? So if you look at it, the known function is called y of x because it is, yeah, the function on the state, and the unknown component is called theta. So if you look at, not x, here we have mentioned q and q dot, which is essentially the state q and q dot. So I r dot is equal to y of q dot theta plus tau, right? Is it okay?
Yes, sir. Yes, sir. It is okay, sir. It is in the form of theta phi dot transpose like that.
Yes, yes. So this is often called linear in parameter form, or in short, LIP, linear in parameter. Okay. There are others which are non-linear in parameters, where you can't separate a function and the known and unknown in a multiplication fashion. Okay. But since this is easily separable, we can do certain things about it. Okay. Now IR dot is y theta plus tau, right? Now, if this theta is completely known, what you can do is you can substitute tau as minus y theta minus kr, where k is a gain, right? And it would have been IR dot is equal to minus kr, and r dot is minus k by I into r. And if you choose k in such a fashion, this is
So we can also add one more. Okay, it is only a function of first order. We can take only one constant of r.
exactly. Yeah, that's why we have considered this filter tracking error. Otherwise, we would have to consider two components, one involving e dot and one involving e, right? Which we
Sir.
had done earlier. So here we have considered this um, IR dot is equal to minus KR. Is that okay? Okay.
Yes, sir.
Now this was the case where theta was known, right? But what if theta is not known? So if theta is unknown, then we take a theta hat, which is a function on t, to be an estimate for theta. Okay. This we would design. Now the objective is to make theta hat go to theta. Okay. And we have to make r go to 0. So these are the two objectives of us, right? So if you look at this equation over here, And we had considered tau to be like this earlier, but since we don't know the value of theta, we can't actually implement this tau. So what we do is we take this theta, and wherever there are theta, I just replace it by an estimate theta hat. Okay, so this is called certainty equivalence controller. Certainty equivalence controller. Okay, is that okay?
Yes, sir.
Okay. Now I substitute this tau in this original equation. So IR dot is equal to y theta minus y theta hat minus kr. Okay. Now what I do is I define a theta tilde, which is the error in thetas, to be theta minus theta hat. Okay. So if you look at IR dot is y theta tilde minus kr. Okay. Now let's look at a Lyapunov function, candidate Lyapunov function, which is v of r comma theta tilde is half ir square plus half theta tilde transpose gamma inverse theta tilde. Now, have you seen this kind of Lyapunov function earlier?
Yes, yes, sir. Yes, sir. Sir has told that one.
Okay,
Yes, sir.
okay, cool, cool. So this adaptive command trajectory you haven't studied, right? So I mean, this method of studying have you studied?
No, sir. No, sir.
No. Okay, so it's a new thing then. Okay, good. So this kind of Lyapunov function is, so anytime you construct a Lyapunov function, you have to study whether it is positive definite, whether it is radially unbounded, and whether it is decrescent, right? So is it positive definite?
Yes, sir. It is positive definite.
Okay. Is it radially unbounded?
Yes, sir.
Okay, because all if r is equal to infinity, r tends to infinity and theta tends to infinity, it is
Yes.
ready, it is infinity. And decrescence is also true because it is not dependent on time, and this is a positive definite function, right? So this is a valid candidate Lyapunov function. Now we compute the v dot. So it is r into I r dot plus theta tilde transpose gamma inverse theta tilde dot. Okay. Now r I r dot, and what was theta tilde? Theta tilde was nothing but
Theta minus theta hat.
theta hat theta minus theta hat. So theta dot minus theta hat dot. Now theta is a constant value. It is unknown to us, but it is a constant, right? So this is 0. Whereas this we don't know yet. We have to design theta hat dot, right? So it is up to us. So we have to choose theta hat dot in such a way that this entire thing is negative definite. So It is nothing but r into ir dot, we can substitute from here, right? So it is nothing but y theta tilde minus k r plus theta tilde transpose gamma inverse with a minus sign theta hat dot. Now we could write minus k r squared plus r y theta tilde minus theta tilde transpose gamma inverse theta hat dot. Now can you suggest a theta hat dot such that these two terms get cancelled out?
Sir, yes, sir. We can suggest, sir.
So it
Uh,
is nothing but gamma.
Gamma, yes, sir.
Yes.
Gamma into k r square plus that one k
No,
r.
no, no. The kr square is okay. Okay term, right? We just have to cancel this term and this term.
Okay, yes, sir. Yes.
So it's gamma transpose into, sorry, y transpose into r.
Yes, sir.
If I substitute it over here, you can see it easily. V dot is equal to minus k r squared plus
Okay, okay. Positive unit. Yes, sir. Yes, sir.
minus this gamma and gamma inverse get cancelled out. So theta tilde transpose y transpose into r. Now this is the transposition of this.
Cancel each other.
They cancel each other, right? So v dot is minus kr squared. Is it positive definite or negative definite? Oh, sorry, it's negative, but is it negative semi-definite or negative definite?
Negative definite only, sir.
Negative definite. Negative definite? Are you
Why?
sure about that?
Because only we have considered r and r dot. So
No, r
ah,
and theta tilde as well
theta
in the
tilde.
Lyapunov function.
Yes, sir. If it is so, negative semi-definite, sir.
This is negative semi-definite, right? But we could use this Lassalle's theorem. So the omega was r square, not r squared technically, but it was uh, r cross r cube, because this theta tilde is a three-dimensional vector. So it contains b, ml, and I. So it's a three-dimensional vector. So and r was means this r was a scalar, right? So this overall omega is this thing. Now what is E? E is the places where V dot is equal to 0. So V dot is equal to 0 implies R is equal to 0. Now we have to show that R dot 0 implies that it is only origin. Right? Origin is the only where it is happening. Right? So R dot is equal to 0 implies that,
Three stands for the three. What is the three stands for, sir?
yeah, so
Here.
what is
R.
the dimension of theta? So if you
Oh,
look at theta
yeah.
over here,
Yeah.
theta is
Three,
three-dimensional vector.
three-dimensional vectors.
So this omega is r due to the radius, I mean filter tracking error, and this is due to theta tilde. Okay.
Yes, sir.
Now I r dot is equal to 0 implies ir dot is equal to 0. Now r was equal to 0 from here. This implies theta tilde is also 0. So origin is the largest invariant subset of E This implies origin is convergent, right? So this result v dot is equal to this, whatever. This system is globally asymptotic stable. Is that okay? Okay.
Yes, sir.
This implies that R goes to 0. This implies E and E dot go to 0, right?
Yes, sir.
This implies Q goes to Q desired and Q dot goes to Q desired dot, which is our original objective. So this was a very long way of saying that we have designed an adaptive controller, and the adaptive controller was here, right? So if you look at this tau, it was easy to miss this tau, but if you look at this tower here, let's see, where was that tau? This tower here, this was the adaptive controller. So if you look at, let me write it down finally. So tau is y theta hat minus kr, and theta hat dot is this gamma y transpose into r. So this is your adaptive controller. And based on this adaptive controller, you can say that this entire system trajectory would track this desired trajectory, right?
Yes, sir.
So this was the adaptive control, one example of it. So whenever you have a problem which is adaptive control related, the first thing you should try to do is to figure out whether this is a regulation problem or a tracking problem. So the first thing which you need to do is you to figure out whether the states have to go to 0 or whether the error has to go to 0, right? So
Sir,
when that,
sir, one doubt, sir, in this discussion. Can you go down, sir, next page?
yeah, absolutely, absolutely.
Sir, here while writing here just above, sir, you are writing directly how error equation, that is R dot is equal to error equation I into R dot. Yes, sir. This
This
I
one.
am having some doubts, sir, here.
Okay, okay. So we have said that E is the places where V dot is equal to 0. Is
Yes,
that
sir.
clear?
Yes, sir. Yes.
So V dot is equal to 0. If you look at here, V dot is equal to 0. This implies minus K into R square is equal to 0.
Yes, sir. Yes, sir.
This implies R is equal to 0,
Yes, sir.
right? Now
So,
the theorem of LaSalle meant that if there is an element on E, it cannot stay identically to the same place except for the origin,
yes, sir.
right? So
Yes,
identically, if it is has to stay there, this implies that R is equal to 0. The R dot must also is not equal to 0.
yes, sir.
So let's look at where the places where R dot is equal to 0. So if you look at R dot is equal to 0, I can multiply both sides by I, and I into 0 is essentially 0. I can substitute the dynamics I R dot is equal to y theta tilde minus kr, which was here.
Yes, sir.
Okay, so we can substitute it over here, and given that r is equal to 0, this entire thing equal to 0 implies that theta tilde is equal to 0.
Yes,
So
sir.
r dot can be equal to 0 only where r is equal to 0 and theta tilde is equal to 0, which is nothing but the origin. So origin is the largest invariant set of E, subset of E.
Yes, sir.
And by Lassalle's theorem, origin is convergent. Okay. So the system is globally asymptotically stable. Global because the Lyapunov function we had considered was radially unbounded. Asymptotic because we have applied this Lyapunov, Lassalle's result. And stability due to the fact that the Lyapunov function is negative, semi-definite, but yeah, using Lassalle's, we have made it asymptotic stable as well. Is that clear?
Yes, sir.
Okay. Cool. So, do you have any other doubts in this entire?
Yes, sir. That is how I into just you are writing in terms of error state, sir. How we are writing uh, that that place where we are getting the error dynamic equation. How we are writing error dynamic equation, sir.
So this filter tracking, this one, right? IR dot is equal to this thing, entire thing.
That I know, sir. That I know, sir. Later, the next step, sir. The next step.
This one.
That I already this one, sir. This one just below that IR dot is equal to Y. Okay, you have directly written. I have confused, sir. Yes, sir. I understand.
I
Yes.
have just
So
replaced the Q and Q dot. Like I didn't write that, but actually Y is essentially the function on Q and Q dot.
later step I into R dot is equal to some theta tilde dot you have written, sir. That
Yeah, so this one, right?
next one, sir. Next step, sir.
This
This.
one, this one.
Yes,
Okay.
sir.
So this part you have understood. So IR
Yes.
dot is equal to Y theta plus tau.
Yes, sir. Yes, sir.
This part you have understood.
Yes, sir. Yes, sir.
Okay. Now, in the earlier case, we had substituted the tau to be minus Y theta minus KR,
Yes,
right?
sir. That understands,
But
sir.
this theta is not known to us.
Yes, sir. Yes.
So what we do is we replace that theta with this theta hat.
That is the yes, sir.
This is the certainty equivalence controller.
We need to estimate, sir. We need to estimate when theta is not known.
Yeah, exactly, exactly. Right? Now
Yes,
I
sir.
substitute this tau over here,
Yes, sir.
y
Yes.
theta minus y
Yeah,
theta
yeah.
hat.
Yeah. Now I got, sir. So, so here this is assumption, sir. That is certainty equivalence controller means when theta is not known, we will take the same form, but theta is substituted with theta cap.
Yeah, 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 exactly. Now, it's not an assumption. We are designing the towers in such a way.
Yes, sir.
If theta was known to us, then we would have used theta. But since theta is not known, we have to estimate it. So we substitute theta with its estimate.
Yes, sir. Yes,
So
sir.
that's the only concept. It's very like elegant way of doing things. Okay.
Yes, sir.
Now I would teach you one concept. Not teach per se, but I think professor has covered it in the class, which is called signal chasing.
Yes,
Signal
sir.
chasing.
Yes, sir. Signal.
Has he covered?
Yes, sir.
So
Complete. Sir has told every signal we need to be bounded or not. We have
exactly,
to.
exactly, exactly, exactly. So our job didn't stop here. We have to show that every signal was bounded. Okay. So if you look at the Lyapunov function, which we had considered v dot is equal to minus, sorry, not Lyapunov function, but the derivative of Lyapunov function, v dot is minus kr squared. So this means that v dot was less than 0, which meant that v of t is bounded.
Yes,
right?
sir. Yes, sir. Yes.
This
When V of
means
t is bounded, the terms associated with V, that
exactly
is,
r and theta tilde are bounded,
yes, sir.
right?
Yes, sir.
This implies E and E dot are bounded.
Yes,
Why
sir.
do I say that?
So since
R is bounded.
v dot is less than or equal to 0, means v dot is finite, sir. So v dot is a function of E and E dot.
Yeah, specifically it's a function on R, and since R is bounded, R was nothing but E dot plus alpha E. R
Yes, sir.
bounded implies E dot must be bounded and E must be bounded.
Yes, sir. Yes, sir. Alpha is a for finite value of alpha. We can take yes, sir.
And theta hat, which was nothing but theta minus theta tilde, right? Because theta tilde was technically theta minus theta hat,
Yes, sir.
and I rearranged that theta hat is equal to theta minus theta tilde. Since theta is bounded,
L infinity. Yes, sir. Theta hat is also L infinity.
theta tilde is also infinity, so this is L
L
infinity.
infinity. Yes, sir.
Now, if you look at the control law, ut is equal to minus y
Into theta
theta
hat.
minus k r.
Uh, this is u of t is also bounded, sir. Since r is bounded, theta hat is bounded.
Yes,
U of t is bounded, sir.
u of t is bounded, right?
Yes, sir.
So hence proved. So all the signals we have considered are bounded, and the r is going down to 0.
Yes, sir.
So this way we can prove that our control law is making sure that all the parameters or all the signals are bounded and the tracking error goes down to 0.
Yes, sir.
Okay, cool.
Yes, sir. Yes, sir. Sir,
So
sir,
yeah,
slides where we can get, sir, as for SARS, SAR is also told the slides is telling the lessons where we can get the slides.
okay. Let me ask Professor Bhasin when I meet him, and I could share that to you. Give if he gives me the permission,
Yes, sir.
and I will do that. Okay. So let me write it down. Okay. So we have 20 minutes left in our discussion. So I can quickly cover a nonlinear system. Is that okay?
Yes, yes, sir. Yes.
Okay, cool. So let's look at a general case. So this is the nonlinear system case, MRAC for nonlinear case. I think he has covered this in class.
Seventh lesson, sir, sir told what are the different types of the non-linearities existing, and in the in that one unmodeled dynamics, how can we specify disturbances? How can sir has told today that seventh lesson, sir,
Okay,
discussed
okay, cool,
about
cool,
parametric
cool.
uncertainty,
Yeah,
unmodeled.
so this is essentially parametric uncertainty. So this is the LIP form, parametric uncertainty.
Yes, sir.
So let's look at MRAC for nonlinear system. So x dot is equal to a fx plus p gx u. So this is oftentimes called a control affine system, control affine nonlinear system. Why control affine? So affine means that it is linear in the variable under consideration. So control affine implies that this system is linear in U. Okay.
Yes, sir.
Now we assume that fx and gx are known. Right. And f is a function from real numbers to real numbers, and g is a function on real numbers to real numbers. Right. Now, the only thing which are unknown are these a and a and b scalars, right? So a, b, which are scalars, are unknown. Okay. Now, how do you solve this? How do you find a model reference adaptive control? So first you have to figure out what is the objective. So the objective is to track a model which is xm dot is equal to am
Into
xm.
plus BM into R.
Perfect. So this is a model reference adaptive control problem, right? So
Yes, sir.
this is the plant and this is the model. Now I would be asking you how to solve this. So first we have to figure out what is the error in these two, right?
Yes, sir. Yes, sir. X minus X dot minus XM dot, that is dynamic.
X, so E is x minus xm,
Yes, sir.
and E dot is
E dot is equal to X dot minus XM dot.
right.
Yes, sir.
So there are two approaches which we can take to do this. One is the filter tracking approach, and one is the normal approach, right? So
Yes.
considering E and E dot.
Yes, sir.
Yes. So which one do you want me to do? So it's completely up to you.
Yours wish, sir. No problem. It is new to me. Both are new to me, sir.
Okay. So we could either consider R, and we could either consider E, E based method, right?
Yes, sir. Your wish,
Uh,
sir.
so actually, the thing is that in this case, there is only a single dynamics. So it's a single integrated system, right? X dot.
Yes, sir.
So there is no need for having this E dot. So E dot is not a state. So E dot
Yes.
is
Error.
directly observed from, I mean, E dot is calculated from the differential equation. So E dot is not a state, and hence the filter tracking error won't work here. Okay, because in the filter tracking error, you had to have the observations for E dot and E, but this is not available to you. Okay,
Yes, sir.
so let's compute E dot, which is x dot minus xm dot. Now I can substitute the entire thing. So here P, here, and here, copy here. Now, so this is a tracking problem because we are trying to track these two different models together, right? Hello.
Yes, sir. Yes, sir.
Yeah, yeah. Sorry, I thought I was disconnected. Right. So we have this E dot is equal to AF plus AFX plus B and so on. Right. Now, can we separate out the unknowns and knowns here?
Yes, sir.
How can we
So
do that?
known values are AM and BM are known values, sir.
A
Uh,
and BM and unknown.
model
So
model.
sorry, yes, you are correct. AM and BM are unknown. Sorry, known to us. So A and B are unknowns.
Yes,
So
sir.
can
Yes.
we write it in this fashion?
Matrix form. Yes, sir. Yes, sir. We can write, sir.
Actually,
So
we
yes,
can't. Actually, we
these
can't because B is multiplied by U, and B over here multiplied by U is actually not possible to handle in this approach. So what we do is we can simply define a control law. So suppose A was known and B was known. Can you design a control such that these nonlinearities get cancelled out and you can place the control?
yes sir, yes sir, yes sir.
Tell me.
We can write U is equal to minus F. U is equal to minus BG whole inverse.
A BG whole inverse, right? Perfect.
BG, BG whole inverse into
So
uh,
since this is a scalar, I can divide them by
yes sir, divided by BG. So minus AF sir,
minus AF
minus AF uh, plus AM XM
plus AMXM,
XM into B into GX. No sir, yes sir. Plus B into BM into R.
right?
Yes sir.
Now I can do one thing. I can take GX out and I can write minus A by B into Fx
Yes sir.
plus AM by B into X
Yes.
plus BM by B into R,
Yes sir.
right?
Yes sir.
Now these three are unknown to us. So this is unknown, this is unknown, and this is unknown,
Yes sir.
right? So
Yes.
we can write K1, K2, and K3.
Yes sir.
Okay. So uh, since this was unknown, so we can define a certainty equivalence controller. This is 1 by gx minus k1 hat
Sir, it is
fx.
XM no sir. AM by B into XM.
Yeah, correct. Sorry. And this is rm. Oh, sorry, this is r. Yeah, perfect.
Yes.
Right?
Yes sir.
Now I can take this entire thing and we can substitute it over here. So when you substitute it, E dot is now let me write the final thing because this is going to take some time. So
Yes.
by simple manipulation, we could write that E dot is AM into E dot
Yes sir.
minus BK1 tilde into FX
Yes sir.
minus BK2 tilde X minus BK3 tilde into R. This is X, not XM. So we substituted, the error is taken over here.
Yes sir.
Okay. So this is the error dynamics equation.
Yes sir.
So it's very simple to see if you substitute. I'm just skipping it right now because it's very long derivation.
Yes sir. Yes.
Okay. Now if I take V over here, which
As
is half E square plus
is plus half plus B by 2.
not B, but mod of B,
Yes sir.
because this this Lyapunov function must be positive definite, right? So
Yes, sir. K1 square plus modulus of B by 2 into 1.
I can explain why I choose this Lyapunov function at a later class.
Yes.
But if I do this, right,
Yes, sir.
and I compute the derivative, v dot is e into this entire thing. So
Yes, sir.
minus mod b
D
divided by gamma 1
gamma 1
into
into K
k1
tilde
tilde.
and
Perfect.
minus K hat.
Perfect. Minus यहाँ I already considered gamma 2 k2 tilde
K
k k2 hat dot
hat
minus b gamma 3
K3
k3 tilde
K3
k3 hat dot,
hat.
right?
Yes.
When I do this, I
Yes.
can compute that if my k1 hat dot is minus gamma 1 sine of b
Yes, sir.
fx into e.
Yes, sir. It cancels out that term.
Exactly, exactly. So this way we choose sine of b into x into e, and
Yes.
similarly k3 hat dot I can do minus gamma 3
Yes.
sine b into re.
R into it.
If
Yes.
it we can cancel these three terms
Yes.
out
Yes, sir.
easily. So this becomes v dot is simply minus am e squared,
Yes, sir.
right?
Yes, sir.
So we can show that the
AM into E square, sir. Actually, AM generally taken as a negative value, sir.
yeah, sorry, yeah, force of habit, yeah, am into e squared. So this am is negative value, as you correctly pointed out. Am is negative, so this is negative semi-definite,
Yes, sir.
right? So v dot is less than or equal to 0. This implies v is bounded.
Yes, sir.
This implies e and whatever these all values e k1 tilde, k2 tilde, and k3 tilde all are bounded. K1 tilde, k2 tilde,
And K3 tilde.
k3 tildes are all bounded,
Yes, sir.
and since v dot is also bounded
Yes, sir.
because v dot contained am into e squared, so e squared is bounded, right? So
Yes.
am into e squared, so a this is bounded.
Yes, sir.
This implies v dot is bounded.
Bounding.
This implies e is square integrable
Yes, sir.
because v is
Function of E square. V dot is a
yeah
function.
function, perfect. So the integration, so v is essentially integration of am e squared.
Yes,
So
sir.
since v is bounded, so this is square integrable.
Yes, sir.
Now, um, in the previous week, we had discussed that if a signal is L2 and L infinity,
Barbellet's lemma.
yeah, perfect. So E is both L2 and L infinity, and E dot is bounded. This implies E would
Oh,
go to 0.
yes, sir.
So this is the way we show that for a nonlinear system, we can
Asymptotically stable.
control, yeah, asymptotically. Not asymptotically stable. Yeah, this is the challenge. The
Globally,
asymptotic stable, no, no, asymptotic stability we cannot comment on k1 tilde, k2 tilde, k3 tilde because these are bounded but not going down to 0.
yes.
The only value which goes down to 0 is this error E. Okay.
Yes.
So this is stable and the tracking error goes down to 0. That we can see.
Yes.
Okay.
Yes, sir.
Yeah. So we have covered quite a few topics today. So I hope this gave you a few examples on how to solve these adaptive
Yes.
problems, right?
We need these notes, sir, that we helps us a lot.
Uh, I would be sending it just in a few moments. After I upload that video, I will be sending it to you
Yes.
in that group,
Yes.
Google discussion groups, and you could also uh, post other questions in that Google group, and we will
Sir,
be
that
taking turns.
Google group, I don't know, sir, that one you are telling. Oh, oh.
Yeah. So when you go to NPTEL SWAYAM course, right?
Yes, yes, sir.
So under my courses, you have this nonlinear and adaptive control, right?
Yes, sir.
So if you look at the web page, there is a post called "Ask a Question"
Yes, sir. Yes, sir. Yes, sir.
tab. You click on that, you would be redirected to that Google group.
Yes, sir. Yes.
You can select a new conversation, and it's a simple mail type of thing. So when you write that, everyone would be notified of that. So we
Yes.
could answer that question, and we could like everyone could see that as well.
Yes.
Okay, so you could do that, or the second thing which you could do is you could in that week lecture, whichever I have been doing that.
Yes, sir.
So under that, you could write this question, and I could answer that.
Yes, sir. Yes, sir.
Now, so on that note, if there is any other question, like any high level question, we have 4 minutes to spare.
No, sir. No, sir. Sir, you are explaining very good, sir. I am learning so much.
Hopefully, yeah, in this course you would learn more such concepts. And okay, so what is your background in this? Why have you joined this course? Like, are you a student of control theory?
No, sir. Actually, I am actually from IIT. I completed my PhD from IIT, and Bhasin sir is my SRC member also. I have
Right,
taken. Yes, sir.
right.
In
So
2000.
you were a faculty of sorry
Yes, sir.
alumni of IIT Delhi, right?
Yes, sir. Yes, sir. And also, I am faculty, sir, where I wish to upgrade my knowledge. So, I am. Uh,
Perfect, perfect. That's very nice to hear. Very nice to hear. So we could have a conversation at a later date. Let me just stop the recording first, and then
yes,
have a small conversation.
yes.